Okay, so this is an introduction to Unit 6, Solutions and Gas Laws. This is the first class. I handed out in class the solubility curves. It's sort of a worksheet, but you don't really have to complete it. I just want to refer to it during this video. And then also practice problems 15.2, which are actually the worksheet that you need to complete. Okay, so we have to learn some vocabulary, and then we're going to learn some quantitative stuff. So what does molarity mean in solution chemistry? Molarity is the moles of solute per liter of solution, and it's one way to indicate the concentration of the solute in the solution. Now, you've already had some of the vocabulary because we did this earlier. A solution in the year. A solution is a homogeneous mixture where the components are uniformly mingled all the way down to the atomic or molecular level. All right. The solute is the substance that dissolves in the solvent. The solvent is the substance that dissolves the solute. Okay, that sounds like a bunch of circular logic. Let's make it simple. Mostly we're going to be doing using aqueous solutions. So the solvent is almost always going to be water. And usually what we're dissolving are ionic compounds. That's our solute. Once in a while it might be a covalent compound like sugar. But for the most part, our solute are ionic compounds. The solvent can also be figured out if you can't figure it out any other way. If you got a solution, if you know which component in the solution has the greatest percent by mass, that will be the solvent. Now, let me go over three very important terms in solution chemistry. Unsaturated. That means more solute can dissolve. So for instance, if you take a cup of iced tea, you put a half teaspoon of sugar in and stir, it's going to dissolve. If you took another half teaspoon of sugar and stirred, guess what? It'll still dissolve. Now, that kind of solution where you can add more solute and it still dissolves is called unsaturated. Now, what about a saturated solution? Suppose we keep adding teaspoons of sugar. We will get to the point that we won't be able to dissolve anymore. Now, there might be some leftover sugar. That's a heterogeneous mixture. Let's get rid of that. So we filter away all the sugar that didn't dissolve. Now we have a saturated solution with it's just tons of sugar dissolved in water. If we were to add just a little bit more sugar again, it won't dissolve. We could stir it forever. It'll go right to the bottom of the container. There's one more type of solution, and this one isn't as obvious. It's called a supersaturated solution. It's the one that I made for you in class and showed you what happens. It will actually turn solid if you add a crystal of the solute to the solution. Why? Because the way it's made is many compounds, ionic compounds, are more soluble at high temperature than low. So we take the water, we heat it up to boiling, we'll take a large amount of the, say, ionic compound, add a tiny bit of water, put it into the boiling water, and when it heats up, that tiny bit of water is sufficient to dissolve all of the ionic compound. Now, we can't touch something with our hand that's 100 degrees Celsius, so we take it out with some gloves, set it down. If you let it cool very slowly, somehow, and I don't even understand this, the crystals will not form even though there's more solid in there than should be, because somehow the crystal doesn't know how to form a crystal. That is, the ionic compound can't form when it stays in solution. Now, if we add a simple crystal to the liquid of a supersaturated solution, the entire thing will turn solid. So that's how you can differentiate these three. Now, this is a solubility curve. So we've got temperature along the bottom. Again, this is just going to be water, so we're going from 0 to 100 degrees. And we're going to have solubility plotted along the y-axis. Solubility is measured in grams of solute per 100 grams of solvent. Since this is water, our solvent is water. Now, if you take a look, you're going to see all these lines. What do these lines represent? Every line represents the saturation line. That is, that's a saturated solution at any given temperature if you've added enough grams to hit the line. So for instance, if it's 60 degrees, and we're looking at sodium nitrate, you get up to about 124 grams. That is the most you can dissolve. It's a saturated solution. Take a look at all the lines that go up. If you look carefully, you will see they are all ionic compounds. All the lines that go down, hydrogen monochloride gas, ammonium ammonium gas and sulfur dioxide gas are all gases, and they all decrease with temperature, their solubility. So all ionic compounds increase solubility with temperature. All gases decrease solubility with temperature. Now, the reason why that's important in terms of, like, I don't know, ecology, think about the oceans. If the oceans warm up several degrees Celsius, what gas that is important for the life of a fish to survive in the water, what gas will decrease in the water? Well, it's going to be oxygen, because as the water gets warmer, the oxygen content will go down. So it makes it a more stressful thing if they are being deprived of some oxygen. The other thing that you really, really need to remember is the units for solubility are grams of solute per 100 grams of solvent. Almost always our solvent will be water. But for comparison purposes, scientists agreed, this is chemists, agreed that we'll always look at the solubility of 20 degrees if we want to compare different substances and try to see if they might actually be the same substance because they dissolve exactly the same amount at 20 degrees C. That's one way we can use physical property to help us guess what compounds are. Now here's that solubility curves worksheet, okay? So for the solubility curves worksheet, one of the things that I want you to do is look at number 1. You should fill that part out. What are the units for solubility? Well, the units for solubility are grams of solute per 100 grams of solvent, in this case water. You will notice these lines are all lines of saturation. One of them is a gas and goes down with increasing temperature. 3 are ionic compounds. They go up with increasing temperature. Now let's see if we can read and get some data off this. What is the solubility of potassium chloride at 50 degrees? So let's go to 50 degrees. Let's go up until we hit the line of potassium chloride. Now remember, that's the most that it can dissolve at 50 degrees. Well, if we do that, and we go over to the x-axis, it looks like it's about 43 grams of potassium chloride that will dissolve in 100 grams of water. So that would be, the answer to question 5. What about question 10, which it looks a little more complicated? Let's say we put 40 grams of potassium chloride into a beaker. We add 100 grams of water and stir at 60 degrees. What type of solution would result? So let's see. Here's 60. Let's go up. Let's see. Potassium chloride. The maximum we can dissolve at 60 degrees potassium chloride is about 45 grams. Since we only dissolved 40, it must be an unsaturated solution. So if we added a little bit more potassium chloride, another half gram, we could actually add up like another 4 grams or so. It'll all still dissolve, indicating that it's an unsaturated solution. Okay. Don't worry, you'll be graphing stuff in this unit. I think the third class this week we have a lab where you'll have to make a graph, so you'll get used to this. Now, what are some of the factors that affect the rate of dissolving? And they're all interrelated. Anytime you have more collisions between solute and solvent, you will dissolve the solute more quickly. Stirring does that, right? You mix them up, the solute and solvent are going to hit each other more, and so that will allow things to dissolve more quickly. Heating, if you heat a solution, or you're trying to make a solution, you heat it up, the particles move faster, and so you'll get more collisions between the solute and the solvent. And the last one's a little harder to understand, but if you increase surface area, you'll get more collisions. Best might be illustrated by thinking about taking a lollipop, putting it into a beaker of water. Imagine how long you'd have to stir that lollipop in the water before all the sugar dissolved. Or you could take the lollipop, crush it up in with a mortar and pestle to powder, take your stick out, and then dump the resulting powder into the same amount of water that you were trying to dissolve the entire lollipop in without breaking it apart. The reason why it will dissolve much more quickly is because you have more surface area, which results in more solute and solvent molecules hitting each other. So when we do the lab later this week, you'll have to grind up the crystals of your solute so that you can get your experiment done in a reasonable amount of time. Now, concentration. Concentration is a general term that quantitatively expresses the amount of solute per amount of solvent or solution. So it's a general term. There's different kinds of concentrations. One is called mass percent. You already know this. let's suppose you have some salt water and you put 5 grams of salt in 95 grams of water, and you want to find out what its mass percent is. You take the mass of the salt, 5 grams, you divide by 100 grams, that's the total mass of the solution, times 100, and you have the mass percent of salt in your solution. Molarity, though, is the one we're going to mostly use. Molarity is, again, just like in the warm-up, moles of solute dissolved per liter of solution. There are 2 other terms, molality and normality. I'll explain those tomorrow. Second class. What molality and normality are, they're not something we're going to work with mathematically, but I will at least introduce you to the concept of what they are. Now, molarity. Molarity is, again, a measure of concentration. For molarity, we use capital M to represent it in chemical equations, and it equals moles, which we represent with a little n, divided by liters of solution. So N is moles of solute, L is liters of solution. That's our volume. So molarity has the units of moles per liter, but we abbreviate moles with a little n, and we abbreviate molarity with a big N, M. So if we have a 5 molar solution, okay, 5 with a big M after it, it means there are 5 moles of whatever the solute is per 1 liter of the solution. Now, see if we can solve this using our little equation up here and rearranging. How many moles of sucrose are in a half liter of a half molar solution? Okay, well, we got to solve for moles. So we multiply both sides by L, not a problem. And then we just plug and chug. So we have a half liter times a half mole per liter, and that'll give us 0.25 moles of sucrose. And because there's only 1 sig fig, we have to round it down to 0.3, or round it up to 0.3. Now here's another example of second key equation. By the way, on your section 15.2 worksheet, I would write molarity equals N over L right at the top. I'd also write the equation from this slide right at the top. This is our second sort of normal equation for solution chemistry. And I would write the third equation, which is for dilutions, which is at the end. Now, what mass of sodium chloride is needed to make 0.515 liters of 2.5 mole per liter solution? Here's my equation. I came up with this, okay? Key formula number 2. Grams of solute equals the molar mass of the solute times the molarity of the solution we're trying to make times the volume of the solution we're trying to make. So let's see, what information have we been given? We have the volume in liters, that's volume. We have the molarity at 2.5 moles per liter, we have that. We can calculate the molar mass. All we need to do that is a periodic table, and it's 58.44 grams per mole of sodium chloride. Then we plug in, so we got the molar mass, we got the molarity, we've got the volume, and multiply across, and we'll see that we need 75.2 grams of sodium chloride in order to make our 0.515 liter solution. And that will be 2.5 molar. Now, what are we going to do, though? Let's think about this. Do we take our graduated cylinder? Let's say we've got a 1,000 milliliter graduated cylinder. It'll be a little bit more than half full, but we're going to use that to measure out our volume. And do we put in 0.515 liters of water and then throw in 75 grams of salt? I don't think so, because what will happen is the salt actually occupies volume even after it's dissolved. So our volume might end up being like 0.525 liters. Then we don't have a 2.5 molar solution. So what we do is we put some water in, dissolve the salt, and then adjust the volume to 0.515 liters. That's the best way to do it. Here's another example. So a student masses 25.05 grams of sodium hydroxide. How many liters can we make of a 0.025 molar solution? Well, I have an abbreviated version of the formula here. Grams of solute times equals concentration in molarity times volume in liters times molar mass. So it's basically the same equation. I just didn't put capital M and capital L there. Okay. We can find the molar mass using a periodic table. Sodium hydroxide has a molar mass of 40 grams per mole. This is per mole. Remember, like x to the minus 1 is 1 over x. Grams per mole is grams over mole. I just wrote it a little, with math, with an exponent. Solve for volume. So your volume, again, will be in liters. Your grams is 25.05. The concentration that we're trying to get to is 0.025 molar, and our molar mass is 40. So we plug it in and solve, and we end up with 25 liters. Okay. Not going to go through this example. You can look through it with the notes if you want. It's basically the same kind of thing, but now we've got a hydrated compound, but it works the same. Now, dilutions. This is key formula number 3. Again, I would write this at the top of your 15.2 worksheet. It's called M1V1 equals M2V2. M is molarity, V is volume. The 1 means initial, the 2 means final. So M is molarity in moles per liter, volume. Volume doesn't have to be in liters, but the units on either side of the equal sign have to be the same. So if V1's liters and you're trying to solve for V2, it's going to come out in liters. If one is milliliters, the other one would have to be milliliters. All right, but let's give an example of how to use this. Okay, so you've got a professor. He walks up to you and he says, I want you to make me 250 mils of a 0.01 molar solution of sodium chloride. He doesn't have any solid sodium chloride though, so he hands you a 5.50 molar solution of sodium chloride in a glass bottle. We call that a stock solution. He also gives you all the glassware you need. The most likely piece of glassware you need would be a volumetric flask that is set for 250 mils. That would be an ideal thing to make your solution with. So what do? First, let's figure out what is M1 and V1 and what is M2 and V2. Okay? We're trying to make 250 mils of a 0.01 molar. Those are the final conditions. So the 0.01 molar is M2, 250 mils is V2. We are starting with a 5.5 molar solution of sodium chloride. That's our high concentration. That's got to be our starting concentration. And then we just have to find out how much of the starting solution we need to make that final solution. So we solve for V1. So let's assign our variables. And what unit will V1 come out in? It's going to be milliliters. Since milliliters is here, V1 will come out in milliliters. So we plug it in, and we've got M2 times V2, that's 0.01 and 250, equals 5.5 molar, that's our M1 times V1. Solve for V1, and basically that just means taking 5.5 and just dividing both sides by it, and then just doing the math in your calculator. So what this means is we only need 0.455 milliliters of our 5.50 molar sodium chloride stock to make this solution. So we'll take our volumetric flask, we'll take a pipette, and we'll pipette into the empty flask 0.455 milliliters of 5.5 molar sodium chloride, and then we will add water up to the 250 mil line. Okay. So that should be it. Now, if you have any questions on how to solve the problems, let me know. I can probably give you an example, but I can tell you right off the top of my head that the first 8 problems can be solved using key formula number 2. You can also solve them using key formula number 1, by the way, so it'll work. Once you get to the last couple of problems, they're a little bit more tricky. I know that number 9 is the dilution problem. Number 10 is one that I'm not going to tell you how to solve it. You just need to think about that, okay?